tomorrow, we schedule makeup for Tuesdays and Thursday, 12 noon at Fort Hall. So for those who completed, who requested for that, I've also shared the information. And uh, I want to say that you continue to pay attention in class. I want to welcome you into new topic that we'll call Chapter 8, Confidence Interval. Statistics is like a story that go on and on and on. We're actually going to build on foundation of Chapter 7. If you really want to understand Chapter 8 that we want to do right now, then you need to have a solid foundation of Chapter 7. You remember Chapter 7 focus on sampling distribution of means and proportions. So Chapter 8 is basically going to focus on that. So that's going to serve as a foundation to what we want to do today. Confidence interval. Okay, so in the outline, today we want to focus on confidence interval of proportion. Maybe next time we're going to focus on confidence interval of means. Of course, you remember in Chapter 7, we focus on sampling distribution of proportion. We also focus on sampling distribution of means. So in Chapter 8, we'll focus on confidence interval of proportion. We're also going to focus on confidence interval of mean. Now, I want us to pay attention now. I want to start again, okay? Because me time to start, the counting, the countdown to mean time to starts now. So I need you to pay attention. The whole idea actually started, from also trying to figure out the unknown population parameter. We want to figure out unknown population parameter. Unknown population parameter could be, what is the average household income in a country? Unknown population parameter could be, what is the proportion of eligible voters that will vote for candidate A? The unknown population parameter could be, what is the true efficacy of a vaccine? So the unknown population parameter, this unknown, it's unknown, and that's why I want to figure it out. And you know what? If we want to get the unknown population parameter exactly, if I want to know the proportion of eligible voters that will vote for a particular candidate in the coming election, if I want to get the exact value of the proportion, I need to study the whole population. I'm going to say that again. If you want to get the exact true value of the characteristics of interest of a parameter, you need to study the entire element in the population. Don't forget, we do not have resources for that. And because of that, what we normally do, because we're limited by budget, we normally take a sample. When we take a sample, then we do estimation. So when you take a look at what I'm actually saying now, when we talk about estimation, estimation happens when sample is involved. So estimation is the process of estimating the unknown population parameter. Process through which you obtain the unknown population parameter using sample information. I want to figure out the unknown population parameter, and I'm only using sample. That's what we call estimation. I'm estimating. And let me tell you this. When I'm estimating, we actually get two types of estimation. But before I'm going to go into two types of estimation, I first want to differentiate between estimation, estimate, and estimator. They are not the same. I'm going to write that down. So like I said, okay, estimation, okay, estimation, estimate, okay, then estimator. I need you to pay attention. The three are not the same. And I want to tell you the difference between them now. Estimation is a process of estimating unknown parameter value using sample information. When you're trying to estimate parameter value using sample information, that's what we call estimation. Okay, estimation means you are working with sample and you want to estimate the parameter of interest. Estimator is a formula that you use. For instance, if I want to figure out the average and I have a sample, I'm actually going to use X bar. You're going to see this X bar equal summation X, okay, divided by N. That's an estimator. So this guy here is an estimator. Okay, a formula that you use in an estimation process is an estimator. Does that make sense? Now, let's say, for instance, I'm actually working on the average and I got maybe I want to figure out the average household income in a particular country, and I got this value. Maybe I got 40,000. Okay. I got 40,000. I got the value that I got is an estimate. Does that make sense? Estimator is the method, is the formula that you use. At the end of the day, the value that came out of estimator is an estimate. The process of using sample information to figure out unknown population parameter value is called estimation. You can say there's a difference between estimation, estimator, and estimate. But let me tell you this. The moment estimator is wrong, estimate will be wrong. Because estimator is a formula, it's a method. There's something in computer that we call garbage in and garbage out. The moment the formula is wrong, then whatever you're going to get from me will be wrong. Now you now understand what we mean by estimation now. And I want to say to you, we got two types of estimation. We got a point and interval. What do I mean by points? What do I mean by interval? A point estimation is a process, okay, or of trying to figure out the unknown population parameter using sample information, and in that process, you're only going to get a single value. That's why I call it a point. Right now, 40,000, but it's a single value. It's a point estimate. I'm going to say that again. In an estimation process where you get a single value, whether you're computing the mean or you're computing the proportion and you get a single value, We call that a point estimate. But let me tell you this. A point estimate could be wrong or right. I'm going to say that again. Getting a single value, even though you've already done everything statistical, like you follow the statistical procedure, okay, and you get a single value, that single value can be wrong or right. It is 50-50. Therefore, we actually need to incorporate uncertainty into sample estimate. Incorporating uncertainty into sample estimate is making it for us to have what I'm going to call interval. Okay. And let me tell you this, if a single value can be wrong, all values in an interval cannot be wrong. And that is why in research in general, when you see research articles, you're actually going to see interval estimates. Because with interval estimate, you have incorporated what I call the margin of error. The margin of error actually enable us, it incorporates what I call uncertainty. It's telling us that we got some uncertainty around the sample statistic in relation to the population parameter. Okay? And that's why the margin of error is going to come in a way that is going to, it's a kind of a bound, a boundary, like a bound that we place on the sample statistic. Let me tell you this. We acknowledge the fact that sample mean is not the same as population mean. Sample proportion is not the same as population proportion. But based on what you've learned in chapter 7, that I call sampling distribution, okay, and in sampling distribution, you learn the law of large number. The law of large number said, and I quote, when you take a sufficiently large sample, sample mean converges to population mean. Sample proportion converges to population proportion. Now, in an estimation process, we get sample mean, we get sample proportion, but you know what? We want it to converge to the population parameter. But let me tell you this, when we say convergence, we're not trying to say it will automatically be the same as that. Because Judge Boss said, and I quote, all models are wrong, but some are useful. I'm going to say that again. All models are wrong, but some are useful. What do I call model? A model is a statistical representation of reality. We use model to depict reality, but model can never give us exact characterization of reality. There's always going to be a gap. But you know what we're trying to do? What you're trying to do is to minimize the gap. We can never close the gap. There's always going to be a gap. And that is the reason when instead of you to work with the entire population and you work with a sample, whatever you get from the sample, you want to use it to represent, okay, the population parameter. But let me tell you this, we're actually going to, it's not as if it's going to be exactly equal to that, but what we can tell the world, the sample proportion, the sample mean, we converge, to the population parameter. So which means we're going to place a bound. The bound that we're placing is the margin of error. Does that make sense? Now, you're now going to see how we're going to get, where is it? You now know what margin of error is talking about. But let me tell you this. And that was why we said, in measuring how well a point estimate, let me tell you this, the point estimate that you got fluctuate. You remember in sampling distribution, if 1,000 researchers should go into the population, if they choose the same number of sample size, if they compute mean or they compute proportion, they will have different results. So which means sample statistic varies, okay? And what measures the variability of sample statistic around the true value of parameter is standard error. Standard error is different from margin of error. Please, I needed to pay attention. I'm seeing a lot of midterm 2 questions now. There's a difference between standard error and the margin of error. The two are not the same, even though the two are errors. The standard error actually measures variability of statistic around the population parameter value. That's what we call standard error. But margin of error will incorporate uncertainty into sample statistic in relation to the population parameter value. Now, how close can we expect our estimate, which is the statistic, to be the truth? We want what we obtain from the sample to be close to the population parameter value. The population parameter value is the truth. And because of that, that is going to lead us to bias. Please, I need you to pay attention. Okay, I need you to pay attention. Bias is the worst enemy of everyone in scientific community. Okay, is the worst enemy of statistician, is the worst enemy of psychologists, is the worst enemy of economists, is the worst enemy of everyone in scientific world who use statistical model. And what do we mean by bias? Okay, and I need you to pay attention now. You know, if you go by the idea of a sampling distribution, if 1,000 researchers should go into the population, they're going to have different value for statistic, right? Maybe we want to find average, and I say each of you should go into the population, take a sample, find the average. Even if you use the same sample size, you're all going to get different results. Now, if I find the mean of different statistic, if that very value is the same as the population parameter value, then your statistic is unbiased. I'm going to say that again. Please listen. Listen. What we want in statistics, what we want in scientific world is unbiased. We want an estimator that will be unbiased. We don't want an estimator that will be biased. What do I mean by unbiased now? Okay, if I have different value of statistic, maybe I have different values for means, or I have different values for proportions. If I find their average, if their average give the same value as the truth, what is the truth? The same value if you give the values of the parameter, then we're going to say that statistic is unbiased. But in a situation where the average of the statistic is not the same as the true value of a parameter, that's a bias. Bias is not good at all. Bias is the difference between, okay, the expected value of the statistic and, you know, the population parameter. And what happens when you have when it is biased? You are likely going to have overestimation or underestimation. We don't want that. We don't want to overestimate. Imagine you conduct a sample, you draw a sample from a population, and you are biased in your selection. Maybe you are biased toward millionaire, toward the rich people in the population. Then you're actually going to overestimate the mean. If you are biased towards those that are below the middle class in the population, then you are likely going to underestimate. Whether you underestimate or you overestimate, that's not good. That is bias. But what we want to do is we want to be unbiased, where we're not going to overestimate and we're not going to underestimate. And that's what I mean. An unbiased estimator, okay, doesn't systematically over or underestimate the parameter. Okay? And therefore, we want an unbiased point estimator. When I say unbiased point estimator, you know what I mean? We want a formula. We want a method that will be unbiased. Does that make sense? We want a formula that will be unbiased, a formula that will not underestimate the mean or proportion, a formula that will not overestimate the mean and proportion. Because when you underestimate and you overestimate, you are misleading the world. We don't want to mislead the world. Let me tell you this. It is not as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. Okay. So, like I said, we want a situation where the sample proportion will be unbiased of the population proportion. We also want a situation where the sample mean will be unbiased of the population mean. Okay. Now, the next thing is, how much does the estimate vary from sample to sample? You remember the other time, if you want to get closer to the truth, you must be ready to increase your sample size. I'm going to say that again. If you want to get closer to the truth, you should be ready to take a large sample size. Okay. Now, if I really want to know, like I said a good estimator, we have a small variability compared to other estimators. Now take a look at this. I said estimator. Estimator is a formula. We could have several formulas. I want to do something now. Maybe I want to get an average now. Okay. I may be thinking of, should I use the mean? Should I use the median? Or should I use the mode? At times, if I want to answer a particular question, there may be so many candidates, formula or method that can be used to achieve the purpose. All those formula, because you use them on sample, we call them estimator. But we want our estimator to be unbiased. And not only that it should be unbiased, we also want our estimator to have a low variability. When I talk about low variability, it means small value of standard error. I want to show you something now, and I need you to pay attention. Okay? I want to show you, take a look at this guy. You know, if you take a look at this guy, where is the truth? The truth is not at the center. You see that? The truth is not at the center. Situation where the truth is not at the center, that is bias. That's a problem. And what do you see the bar? The bar are scattered. Oh my God. Oh my God. This has a double tragedy. Number one is bias. Number two, large variability. We don't want this guy. Do you see what I circle right now? That's a real problem. It is bias because the truth is not in the center. And not only that, the bars are dispersed, more variability, double tragedy. But take a look at the second one. Okay, you take a look at this guy. Oh my God, this is an ideal situation. This is what we want. We want it is unbiased, the truth is at the center, and not only that, low variability is shrinking. This is what we want. Does that make sense? Which means here, it is unbiased and the standard error is very small. That's why you have small variability. Standard error measures precision of statistic. Precision, how precise statistic is. I'm going to show you another picture now. Take a look at this guy. What happened here? Oh my God. The truth is at the center. It's unbiased, but it has a large variability. It is not only, when I'm talking about the properties of a good estimator, when I'm talking about property of a good estimator, number one, it has to be unbiased. Number two, it has to be efficiency. And what do we use to measure efficiency? Low variability. When you have a large variability, this one is trying to say it is unbiased, but the variability is much. We don't still want that. We don't want it. Does that make sense? Now, I needed to take a look at this. Okay. This is bias. The truth is not in the middle, but the variability is low. Okay, we don't still want this. And the ideal one that we want is this guy here. This is the ideal one. Okay, unbiased, and the variability is low. That's what we want. Okay, now you now see what we want right now. I want to go into interval estimation now. Now, why do we go from point estimation to interval estimation? We go from point estimation to interval estimation. Don't forget, a point estimation will give you a single value. A single value could be wrong or right. A single value could be too high, or it could be too low. And you know what? We don't want a situation where you have committed a lot of resources to the research only to be let down by poor statistical tool. And because of that, we're going to consider what we call interval estimation. Now, let me tell you this: the interval estimation, if I want to construct an interval, for my sample now, for whatever, it means I need a range. I need a range, and that very range of values will be computed from sample, okay? And in that very range of value, it is believed that very range will capture the true value of parameter. And what am I going to use to construct the interval? Oh my God. If I want to construct the interval, I need a combination of a point estimate and the margin of error. I'm going to say that again. If I want to compute the interval, I need a combination of a point estimate and the margin of error. The margin of error is the one that incorporates uncertainty into the sample structure. It's going to consider error to the right, and it's going to consider error to the left. And that is the reason why we're going to do plus or minus. Statistics is like a story. I need you to take a look at this example. According to the 2012 Resident Satisfaction Survey, 32% of a Minneapolis resident felt that public safety is among the biggest challenges of the city in the next 5 years. Considering the reported margin of error of plus or minus 3%, find an interval estimate for P. Now, I need you to pay attention now. I want to tell you the significance of margin of error. The margin of error will tell us how reliable is the mean. It tells us how reliable is the statistic. It tells us how sample information reflects the overall view in the population. Now, I want to, we are in election season in the United States, and I'm going to use this example. Let's say, for instance, a candidate A. Okay, we have a candidate A and candidate B, and they said candidate A has 49% of winning the election, okay, and candidate B has 47% of winning the same election. If you are a supporter of candidate A, don't celebrate yet. You know what you're going to be looking for? You need a margin of error. I'm going to say that again. You need a margin of error before you celebrate. Okay. Now, I want to tell you this: if the difference between A and B, I need you to listen now. If the difference between A and B is more than margin of error, that will be too close to call. Now, for instance, let's say the margin of error is, let's say it's plus or negative 3%. Please, I need you to pay attention. What happened here? The candidate A lead candidate B with 2%, but that very 2% is less than the margin of error of 3%. Theoretically, there is possibility this candidate B could win the election as well. You know, at times when you listen to news, when election, particularly they do that in the United States, when election have not been concluded, election is still going on, and of course they can make a projection. And that's how you're going to say, oh, CNN is going to say, okay, now we can make a projection that this person is going to win. Before they can make that projection, the difference between the candidate A and B, that very different has to be less than the margin of error. Because you know what this guy is trying to say here? Let's take a look at this guy. This guy is trying to say the candidate B can have 50%. Because when you add +3 to 47, and that candidate B can also have, the lowest can have 44%. Then for candidate A that has 49%, if you add +3, it could have 51, and if you subtract 3, it could be 46. Election is too close to call when the difference between the candidates is actually less than the margin of error. So whenever any forecaster tell you and give you an estimate, these are point estimates now. Then you need to ask for, what is the margin of error? Does that make sense to you, everyone? Okay. Now I'm going to go into this as I'm going to come back into this example right now. Okay, 32% when in the survey, okay, actually felt public safety is among the biggest challenges, and they have a margin of error of plus or minus 3%. And I want to construct a confidence interval. I need my margin of error to construct a confidence interval. Okay, now take a look at this. This is the point estimate plus or minus the margin of error. And right now, I got that. Okay, now we believe. Now, let me tell you what this is trying to say. Okay, it's trying to say, instead of you to just say 32% of Minneapolis residents felt that the public safety is among the biggest, that 32% could be wrong or right. It is safer to say it's going to be between 29% and 35% because it is not, even though a number between this could be wrong, but not all of them. Okay, we are confident that the interval will contain the true value of parameter. Does that make sense? Okay. Now, I told you the significance of margin of error. It measures how a point estimate is likely to be in estimating parameter. So it's very, very important when it comes to statistical analysis and the research world. But let me tell you this. What of in a situ, how do we compute the margin of error? You know, in this particular question now, you were given, how do we compute the margin of error? Oh my God. If you want to know how we compute the margin of error, then it depends on what you are working with. Are you working with proportion or you working with mean? If you are working with proportion, you've done it before. If you are working with proportion, okay, if I want to compute the margin of error, okay, now listen now. Margin of error and standard error, they have relationship mathematically. Okay, when I multiply z-score by standard error, I got margin of error. When I multiply z-score by standard error, I got margin of error. I'm going to go, but before going there, let me talk about confidence interval for proportion now. We're talking about proportion, and we want to construct a confidence interval for proportion. If you look at example 8.3, we want to estimate the proportion of contracts in a city, okay, that are awarded to minority-owned firms. We take a random sample of 389 contracts from the city and find that 58 were awarded to minority-owned firms. Now, when you take a look at this, out of a sample size of this, they're talking about certain characteristics of interest. This is actually a question on proportion. So which means the interest is on the number of contracts awarded to minority-owned firms. Now, our goal is to use sample information to construct a confidence interval with a confidence level of 0.95 for P. Now, whenever we open an interval, whenever we describe something in an interval, we need to associate confidence. Okay, we could say we are 90% sure. We could say we are 95% sure. We could say we are 99% sure. Whenever we are constructing a confidence interval, then we must associate that with a level of confidence. What are we trying to say? What do we call the level of confidence? I need you to listen right now. Okay, if I say I'm 95% confident, you know what that means? What that means is if I have opportunity to go into population 100 times, please, I need you to listen. We didn't go into population 100 times. Okay, but I want to tell you what confidence interval means. Okay, you know, which is like the probability or the chance that the true value will lies. So it means if I have opportunity of going into the population 100 times, and in each time I compute the confidence interval, which means I'm actually going to have 100 confident intervals. If I'm 95% confident, then it means the true value of a parameter will only lies in 95 out of 100. If I say I'm 90% confident, it's only going to lie in only 90 intervals out of 100. If I say I'm 99% confident, then it means I'm going to have 100 confidence. The true value of a parameter lies in the 99 out of 100. Now, if I want to do this, the question said, what is the sampling distribution of p-cap? You can see now, if I want to listen to me now, I need to listen now. If I want to construct a confidence interval for a sample proportion, I actually need to start from the sampling distribution. And that was why I said in this particular chapter, chapter 8, we're building on the solid foundation of chapter 7. They got a very strong connection. Now, the question is said, what is the sampling distribution of p-cap? The sample proportion of contracts that will be awarded to minority home firms. Then, of course, you know, if N is large enough, we've done this before in chapter 7. If N is large enough, you know the meaning of this. The mean of p-cap. You know, I told you p-cap is a statistic that varies. If I have statistic that varies, what is the average of that is P, which means the average of statistic that varies is the population parameter. You know what that means? Unbiased. That means unbiased. If the mean, don't forget, when you have a normal distribution, the first one represent the mean, the second one represent the standard deviation. So what we mean here, if I have several values of p-cap, then the average of that will give me the population parameter value. That's a non-bias that we talk about. But remember, we don't only talk about unbiased, we also talk about variability too. I showed you a picture the other time. What measures the variability of p-cap around the true value of P is this guy. This is the standard error now. This is the mean of this guy. Why this guy is the standard error for that guy? We did that in chapter 7. Now, what is the next thing to do? Okay, now, you know, p-cap plus or minus margin of error. How do we compute margin of error? Oh my God. If I want to compute margin of error, I need a z-score, then I need the standard error of the p-cap. Please, I need you to pay attention now. We're getting there. Okay, now, how do I get a z? Oh, if I want to get a z-score, then I need a level of confidence. Whenever anybody asks you to construct a confidence interval, they're going to say, okay, use 90% confidence level, or use 95% confidence level, or use 99% confidence level. Now, because here they're talking about how many? Okay, 95%. You know what I'm going to do to get my Z in R? If I want to get my Z score, I'm actually going to use QNOM. You remember? If I want to get a Z score, I got to use a QNOM. Okay? You're going to use a QNOM. But QNOM here into 1 minus alpha divided by 2. Now, what is my alpha now? Okay, my alpha is 1 minus confidence interval. Now, if the confidence interval is 95%, that means it's 0.95. Okay, what is 1 minus 0.95? That would be 0.05. If the 95% is a level of confidence, then 5% is a level of statistical error. So if because they mention 95%, this guy is going to be 0.95. Okay, and if this guy is 0.95, what is 1 minus 0.95? My alpha will be 0.05. Alpha in statistics actually means the level of statistical error, or you call it the level of statistical significance. The level of significance. Now, I will now come here. I'll put my alpha in. I'll put, for me to get a Z-score. So what I'm trying to tell you now, if you do 1 minus 0.05 by 2, it will give you 1.96. It's going to give you this guy. Now, when you get 1.96, you're going to put it here. Multiply by the standard error. That will give you the margin of error. That is where we compute the margin of error. If you want to compute the margin of error, okay, you need a standard error for the proportion. And not only that, you need a Z-score. And for you to get a Z-score, the formula is Q norm into 1 minus alpha over 2. And now are you going to get your alpha? Your alpha will be 1 minus confidence. They're going to give you the confidence level. Okay, now that is how we're going to get that. Okay, now standard error, I told you. The standard error is actually this guy. For proportion, it is P cap into 1 minus P cap divided by N. That is standard error. Okay, that is what we mean by standard error. Now, let's just see how it's going to be. Oh my God. You know what is going to happen here? You know, the margin of error, I'm subtracting from the P cap, and the margin of error, I'm adding to the P cap. Take a look at that, which means I actually consider error to the left and the error to the right. Now, if you want to base it on the question they gave the other time, if you want to base it on this guy here, you know, the sample size is, they awarded 389, and 58 of those contracts were awarded to minority-owned firm. Now, how do I compute my P cap? If I want to compute my P cap, please pay attention. P cap is actually going to be X divided by N, where S is the number of the characteristics of interest, in this case 58, and N is 389. So your P cap would be 58 divided by 389, and that is what you're actually going to see. Give me 1 second. That is what you see here. Do you see that? That's a P cap. And the moment you get your P cap, okay, you want to use this guy here. So you're going to see that what you are plugging in, your P cap is what you are plugging in inside the square root. Take a look at that. You know, P cap into 1 minus P cap divided by N. Where do we have the 1.96? Don't forget, they will actually give you the confidence interval. When they give you 95% confidence interval, of course, I got that 1.96 by doing a Q norm of 1 minus alpha over 2. And in the end, I want you to see results. Now, this is the interval. Okay. Now, if I want to interpret this interval now, I'm actually going to say on average, approximately 95% of the samples drawn from the population will produce a confidence that contain the true value of the proportion. Okay, and the true value of a proportion here now will lie between 11.4% and 18.4%. It's always good to have your results in an interval. It's going to be dangerous when you just focus on a single value. A single value could be wrong or right. That is not going to be okay in research, where you spend a lot of money, a lot of resources, and at the end of the day, you make use of a point estimation process which could be wrong or right. And that is the reason why it will be safer to you consider an interval for your result, because the interval is always going to contain the true value of parameter. Okay, and that was why finally, before I go today, this is the real interpretation. Now I said, suppose an equal opportunity law require at least 20% of all city contracts go to minority owned firm. What information does the confidence ever give us in the context? If they say, okay, at least 20%, but when you come back here, okay, do we have at least 20% here? Okay, it's like a violation. Okay, the confidence interval is actually going to open our eyes to a lot of stuff. And I said, we are 95% confident that the true proportion of contract that go to minority firm is only between 11.4% and 18.4%. It is unlikely that the true proportion of contract that go to minority owned firm is at least 20%. This is where I'm actually going to stop today. Make sure you all stay safe and have a lovely day. See you on Wednesday. Eyes that more need to be. You understand what I mean? So, it's also to be in the confidence and the confidence in the hypothesis was good. This is the map. How are you? I'm good.